Hello and welcome in the session of Engineering Materials and Metallurgy. Today we will discuss about the one of the important non-ferrous material or metal, that is a copper and copper alloys. So the copper alloys have a electrical and mechanical properties, good electrical and mechanical properties. Then corrosion resistance, thermal conductivity, and wear resistance. The applications of copper and its alloys are in electronic components, then springs and heat exchangers. Then brass is the alloy of copper and zinc, and bronze is an alloy of copper and tin. So in brass, again there are some types, that is alpha brass, beta brass. Then bronze is the alloy of copper and tin, that is armitage bronze. Next, the classification of the copper and its alloys are given below. So initially there will be a pure copper, and second one, when pure copper is allied with the alloying elements, then we'll get the copper alloys. So there are mainly three types of the copper alloys. First is the brasses, second is the bronzes, and third is the cupronickel. So brasses further treated by a deformable alloys, that is forged alloys. Then second one is the cast alloys. Bronzes are further classified in two ways, that is a deformable or forged alloys and cast alloys. Then a designation system of copper and copper alloys. So the designation is a pure copper to copper, ETP, etc. Then deformable copper alloys are denoted by copper CuZn 36Pb3. Then copper cast alloys are denoted by G-CuSn10. Type of the casting, GS stands for sand casting, GM stands for die casting, GZ stands for centrifugal casting, then GS stands for constant casting, and GP stands for pressure die casting. Then conditions or properties based on designation after main designation, that is EN1173 letters. So A will be the for the elongation, so that will be, for example, copper OF A007. Then B for the bending strength, for example, copper SN8-B410 410. So that will be the bending strength of the copper 17 alloy. Then D is the drawn without mechanical properties. G is the grain size, that is nothing but copper zinc alloy, copper zinc 37 alloy with the grain size 020. Then H for the hardness, either Brinell hardness or Vickers hardness. For example, copper zinc 37 alloy with the hardness 150. Then M as a manufacturing condition or method without mechanical properties. Then R is the tensile strength. So for example, copper zinc 39 Pb3. So R500 will be the tensile strength 500 Newton per mm square. Then Y yield strength. So for example, copper zinc 30 Y460, that is nothing but yield strength 460 Newton per mm square. So this is the designation system for copper and its alloys. Next is a magnesium and magnesium alloys. So it is denoted by the M, capital M into suffix G. So Mg is the designation for the magnesium. So magnesium is the lightest metal. Alloys are in structural and non-structural applications. Then typical uses of magnesium alloys are in aircraft and missile components. Then also has a good vibration and damping characteristics. The typical properties and typical form of various wrought magnesium alloys are: it is designated by the series AZ. The composition present is the aluminum, zinc, manganese, and zirconia. Then condition, then ultimate tensile strength, then yield strength, then percentage of elongation, and typical method of the forming. So first alloy, magnesium alloys, is AZ31B, which contains 3% of aluminum, 1% of zinc, 0.2% of manganese. There will be no zirconia. Then UTS is a 260 megapascal. YS, yield strength, is a 200 megapascal. Percentage of elongation is 15 mm. And typical forming process is a extrusion process. If S24 series is there, then 290 will be the ultimate tensile strength, 220 is the yield strength, 15 is the percentage of elongation, and the typical forming process is a sheet and plates. Next type of magnesium alloy is AZ80A, which contains 8.5% aluminum, 0.5% zinc, 0.2% manganese. Then condition is a T5. Ultimate tensile strength is a 380. Yield strength is also same 380. Elongation is quite less. The process is extrusion and forging. In that same series, S24 is there, which contains the ultimate tensile strength and yield strength 255. Percentage of elongation is 8 mm, and type of form is a sheet and plates. The next series is a ZK60A. So no aluminum is there. Zinc is 5.7. No manganese is there, but zirconia is 0.55. Then condition is T5. Ultimate tensile strength and yield strength is 365 megapascal. Percentage of elongation is 11, and typical forming process is extrusion and forging. So this is the properties and typical form of the various wrought magnesium alloys. Then why magnesium is used commonly? Because it has a lowest density structural alloys, which has a 1.738 gram per centimeter cube is the density. Then it has a high specific strength. Then it is superior damping properties, that is it can absorb the vibrations. Then it has a excellent castability. Then it is highly recyclable. Then it has a good machinability. Then good weldability under inert atmosphere. So these are the important properties of the magnesium and its alloys. That's why these are used in the various applications. In applications of magnesium alloys, so sporting goods, power tools, industrial machineries, engine components, computer and electronic products, then other including aerospace application, then automotive applications, magnesium casting industry, road maps, automobile parts, then human body parts, then operation instruments or various rods or joints inside the human body. These are the applications of the magnesium and its alloys. Then magnesium sheet metal. So the General Motor innovates the process of making lightweight, corrosion resistance magnesium sheet metal. Structural panel is expected to help make the vehicle more fuel efficient. So it is a 75% lighter than steel and 33% lighter than aluminum. Then magnesium and magnesium alloys. So the pure magnesium having a melting temperature 649 degrees Celsius, a density is 1.740 gram per centimeter cube. So lightest among all engineering metals. The magnesium alloy contains the magnesium and manganese up to 2.5%. Then magnesium, aluminum and zinc, which contains 10% aluminum and 5% zinc. Then designation of the magnesium. So for deformable and cast alloys, MgMn2 for the deformable, for example, and for cast alloys designation is MCMG aluminum 8 or the material number MC 21110. Then magnesium deformable magnesium alloys applications are corrosion resistance, weldable, cold formable, containers, car, aircraft and machine manufacturing. Then second, magnesium cast alloys, the applications are good castability, dynamically loadable, car and aircraft manufacturing. Next is the titanium and its alloys. So the pure titanium having the melting temperature 1660 degree, then the density 4.54 gram per centimeter cube, then very active to oxygen, carbon and nitrogen. So the 2x is the hardness increases. Then titanium alloys are the titanium aluminum alloys, 4 to 6% aluminum, that is called as alpha alloys. Then titanium aluminum along with the chromium, vanadium, copper, molybdenum alloys, so that is called as alpha plus beta alloys. Third one is the titanium aluminum along with the molybdenum, then Cr, that is chromium, and zirconia Zeta alloys. So these are called as the beta alloys. Then titanium and its alloys. So titanium is expensive. It has a high strength to weight ratio and high corrosion resistance. Used as a component for aircraft, jet engines, and racing cars and marine craft. So these are the commonly used applications of the titanium and its alloys. Then here are some properties and typical applications of wrought titanium alloys are given. So 99.5% titanium condition is annealed. The applications are aircraft, airframes, aircraft frames, chemical, then marine applications, heat exchangers, etc. Similarly, 5Al2.5SN, 6Al4V, that is aluminum, vanadium, titanium alloy. So the temperature and applications are given here. Then percentage of elongation is given. Ultimate tensile strength is given. Yield strength is given. And here temperature in degree Kelvin is also given. Then applications of the titanium alloys in aerospace industry. The specific uses are jet engine parts, airplane bodies, rockets, satellites, missiles, compressors, fan blades, landing gears, flaps, spoilers, engine compartment, wiring, wing bearing, then fuel tanks and boosters. So these are the special applications of titanium alloys in aerospace. Then in chemical industry, electric tanks, reactors, distillation towers, concentrator separators, heat exchanger equipments, then sodium carbonate, plastics, petrochemical metallurgy, salt refining industries, then vessels, pressure vessels, then propellers, water jets, seawater heat exchanger system, vessel pumps, valves and pipes. Then ocean engineering, desalination pipes, offshore oil drilling pumps, valves and pipes. Then in medical fields, artificial joints, dental implants, orthodontics, pacemakers, then cardiovascular stents, surgical instruments, then sport industry, golf heads, tennis rackets, badminton rackets, cues, hockey sticks, sky poles, ice skates, etc. Then daily use application, frames, watches, walking sticks, fishing rods, kitchenware, digital product shelves, crafts, etc. Then in architecture, roofing, exterior walls, then signs, fringe, pipes, etc. Then in automotive sector, exhaust systems, silencer system, springs, connecting rods, and bolts. So these are the specific uses of the titanium and its alloys in the industry. So thank you for watching the remaining types of alloys, that is aluminum alloy, then copper alloys, magnesium alloys, and titanium and its alloys.